Now, we do know that a couple of things. We know that AX0 really implies, as we've already said, that these two velocities, of course, have to be the same. But there's really only one equation. And that equation, of course, is that, as we've already talked about, that it has to be this equation right there. And then what you're seeing here is that now, when I talk about my y, I get minus g here. So this then tells us that we have the free fall. And when we look at the free fall equations, there's always these equations right here. And then finally, our last equation, which is this guy. So there's really, to solve all these problems, you have 1x and you have 3y. And as before here, we're going to use the kinematics table to get a sense of these things here. But I really want to go in and I want to start talking about some of the things that we should really be paying attention to. So what I want to do here is that I want to make a series of remarks to try to decipher what we got to do. Again, as we've done before here, that there is no mixing of x and y components. So when I look at the x equations, right? The x equations tell us only x variables and what? Time. When I look at the y equations, I see only y variables and what? Time. So what you're seeing here is that these two sets of equations are only connected by time. So in other words, finding time in one is also finding time in the other. So determining time in x equations is also the same in y equations. Now, what you're going to find here is that we're going to be shooting things, and we got to be really careful of when we talk about when is it in projectile or free fall motion, and when is it not. Okay, so I need to really address these things. So when is an object in projectile motion? Well, let's look at an example. Let's look at two examples just to be careful here. So the examples I want to think about is that, let's say, shooting a cannonball and when you're thinking about shooting a cannonball, you could imagine that I have a cannon, and let's say it looks something like this. And then, of course, in here in the belly of the cannon, inside the bore, is a cannonball. So what you typically find here is that in the old days, you could imagine that you come in here, you have some wick, you have some fire that you ignite the wick. And what you're going to see here is that while the cannon is in the cannonball. Excuse me, while the cannonball is in the cannon. So if I'm looking at this distance here from here to here, we could see that while the cannonball is inside the cannon, the ball is not in free fall. So in other words, what this is really telling me here is that we cannot apply projectile motion equations. You cannot apply them. Only after the cannonball has left and it's now outside of the cannon, then what we know here is that once it's outside, now there's an acceleration in the y direction that's minus g. So what we say here is that once the cannonball leaves the cannon, can we apply projectile motion equation? You have to be in free fall. Another simple example is about jumping off the ground. Okay, what about jumping off the ground? Well, what do you got to do in order to jump off the ground? And so what you're seeing here is that if you're going to jump off the ground, what you typically do here is that you do what? You come in here and you bend your legs like this, and then you're preparing yourself to push off. And so what you're seeing here in this situation, what you're doing here is that you are accelerating yourself with your feet as you push off the ground. But note, this is not the acceleration due to gravity. So it is true that you are now moving upwards with some acceleration due to your feet here, right? You're moving in the upward direction here. It is only after you leave the ground here. So you are not in free fall here. It's only after you leave the ground. And you're moving in the upward direction like this. Then what you find here is that suddenly you are now in free fall and you are accelerating as you're going there. So what we say here is that the moment your feet leave the ground, you are in free fall. And so therefore I can apply my projectile motion equations. Now note that this is just vertically, but you could imagine that somebody's running horizontally and then jumps. And that's really the situation that I'm talking about. So I find this happening a lot when in problem solving that occurs. So we want to be really careful about that. So let's move on to the next thing here. The next thing that we want to do is that we want to talk about decomposing the initial velocity vectors. And that really plays a very, 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 very big role. Okay. So let's go look at that situation here. So the next piece that we want to focus on, let me find my mouse, is that would be the third thing here, is that we want to talk about decomposing the velocity component. One of the most important things here. And it turns out that there are three cases to consider. So let's look at these guys here. Let's look at case one. What happens if you have a horizontal initial velocity? So what I imagine in this scenario here is that I'm going to assume here that we have an initial, nope, not velocity, an initial speed of 50 meters a second. Why 50 meters a second? It's arbitrary, just arbitrary. So what I imagine here is that I have a table, okay? Now, when I'm thinking about my table here, I imagine that if I have a horizontal speed here, what that really means here is that there's a ball rolling off the table. And as it rolls off the table here, I want to look at its initial speed. Its initial speed in this case here is going to be like that. And because this is a vector here, that means it has an initial speed in the x and an initial speed in the y. So if I set up a coordinate system, right, where this is y and this is x here, what you're seeing here is that the full velocity is, of course, in the x direction. So clearly the initial speed is this, and you can see that v initial y is 0. So when I look at my components here, what you're seeing here is that I have the initial x and y, and according to our definitions here, since I'm measuring things relative to the x-axis here, you could see that the angle in this case has to be 0 degrees. So if I come in here and I put 0, clearly this gives me 50 meters per second, and sine of 0 is 0. So in other words, there is no y component, there's only an x component. So when I go and I look at my initial velocity, in this case, it's going to be 50 meters per second. And in this case, it's going to be 0. Now that's going to be important here because when we start to look at these guys, in terms of our equations are concerned here, you could see here that when I look at my data tables to organize information here, one of the most important pieces is actually putting down the initial speed here. And what you're seeing here is that if this is the initial speed, since the acceleration is 0, this will be the final speed in this situation. But if I look at this here, my y velocity initially is 0. So I have to have the ability to put in those quantities here. Okay, that's the first case. So we just did the first case. Let's go look at the second case.
So I have a question on that. On those ones, so the second that it starts to or the moment that it starts to reach off the table, at that moment, there's no velocity in the y, but then your next one will have it because you have acceleration at that point, right?
Exactly.
Okay.
And even though I didn't write this down, the fact that I have this, right,
Tells you your final.
Tells you that the split second later, Vy is not 0.
Got it. Yeah. Thank you.
So let's go to the next case. So in this case here, we're going to have an upward angle. initial velocity. So when I'm looking at this thing here, you could imagine, again, if I have my table, and then I'm shooting my ball this time. But what I'm doing here is that when I shoot it, I'm now shooting this thing with some initial velocity that looks like what here? Well, I'm going to shoot it with some initial velocity like this here, where you could see here is that there's some angle that I'm going to measure this thing from. Right? So there's some angle. Now, for just the sake of simplicity here, I'm going to just give some arbitrary values. We started with 50 meters per second earlier, and for some odd reason, I'm going to pick an angle of 37 degrees. Now, could I pick some other angle? Of course I can. But the thing about it is that, remember, these initial velocities, I'm trying to make a big deal out of this, because there's going to be 30% of you that are going to get the initial velocities incorrect on quizzes and exams. And it pains me to go in and take points off for this, but I'm telling you, I'm talking to you 30%. That's it. Oh yeah, the initial speed is 50 meters a second. So then I'm going to go deposit these in the X and the Y. And I'm telling you right now, that is incorrect. I'm talking to you 30%, not to make that silly mistake. So I'm going to go through this slowly and methodically to try to get to those people here. So let's go do that. So when I'm looking at this thing, again, I set up a coordinate system. And here's my coordinate system. I look at my velocity. And remember, velocity means two things. Magnitude, and it means what? Direction. So there's two pieces, right? Two pieces of information. We are not arbitrarily giving you two pieces of information just for the hell of it. You need it to set up the problem correctly. So let's go check it out. So what this means here is that if I project this guy onto the x-axis, we see that there's an x velocity. If I project this onto the y-axis, you see that there's a y component. Let's go calculate these things. So if I have a vertical angle, you could see that that angle is in the what? It's in the first quadrant, so both components should be positive. In other words, this tells us here that Vx is positive and Vy is positive because it's in the first quadrant. Right? Just as we would expect here. But then we got to go calculate it. So let's go calculate this thing. So if I go calculate this thing, it tells me what? Okay, I have V initial x should be V initial cosine of what? 37 degrees. So this is 50 meters per second, cosine of 37. So this guy gives me a value of what? Plus 40 meters per second. And then I go to the y component and I do the exact same thing. But this time this will be 50 meters per second times the sine of 37. And what am I going to get? I'm going to get a positive 30 meters per second. So what does that mean? Again, I go to my table. And when I look at that x component, I don't put in 50 meters a second. I put in what? 40 meters a second. Why? This is vector motion. So I'm going to come in here that this must be true because the acceleration is 0. And then I have my y component. It's not 50 meters, it's what? 30 meters. So when I come in and I set up my table, I look at that initial velocity, that's the important piece. I'm really focusing on this guy right here. I'm going to put in what? I'm going to put in plus 30 meters per second. Note, this is not 50 meters a second. You need those components. So there's one last case that we want to go look at. And let's go look at this thing here. Case 3. This time, we're going to have a downward angle velocity. And so what happens this time? Well, in this case here, you could imagine that we have a ball that we're shooting. So when I'm shooting this ball here, this time what I'm going to do here is that I'm going to shoot it in the downward direction. So again, this guy is 50 meters a second. And because of the way I'm setting up my coordinate system, I'm going to choose the same angle as 37 degrees this time. So when you're looking at this thing and I set it up, well, look at my velocity vector. You can see that it's pointed in what? The fourth quadrant. Because it's in the fourth quadrant, we already know here that the x part of this vector is going to be pointed in the positive direction, right? There's my projection. You could see that that guy is going to be positive, but if you look at our standard y component, you could see it's pointed in which direction? In the negative direction. So that means this guy is negative. So you gotta pay attention to the signs here. So in other words, when I go and I compute these guys, because we've already computed this guy here. Now, I know that this angle here is going to be negative, but cosine is an even function. So I'm going to get plus 40 meters a second for the initial in the x direction here. But if I look at the y component, sine is an odd function. So that negative sign in the sine is then going to give me what? It's going to give me minus 30 meters a second in the y direction. So you got to pay attention to that sign. So where's that sign going to go? Instead of being positive in the table up above, it's now negative. So this becomes super important of how you deal with the vectors here. It's like, it's one of the most important pieces here. So we just started talking about the 3 cases that we were just looking at, right? We talked about how to look at horizontal initial velocities. The initial velocity in the y direction is 0. Of course, in the x direction, it's going to be all of it. It's going to be all 50 meters. When we get into the upward angle, you start to see the distribution of the velocities. That is, there's a projection on the x and the y. Those are going to give you positive components. And when we're looking at the downward angle, the big difference is that the y is negative. It turns out that the initial velocity plays an extremely important point in determining what's going to happen. And what I want to do now is that I want to come in and want to start looking more details of the velocity vector behavior of projectiles. So let's go look at that. So now we want to look at the initial velocity impact on projectile behavior. And so what I'm going to do here is that I'm going to set up I'm going to use an applet called by a guy named Phys. So I'm going to use, he's a German guy. And he has, I'm going to use his projectile applet. This guy's a super nice guy. And you know, he's very open to letting people actually modify his applets, which I think is really amazing. And what we're going to do here is just like how we fixed it at 50 meters a second. What we're going to do here is that we're going to have a fixed speed V initial of 10 meters per second. Okay. And what I want to do here is that I want to set you up before I actually get to the applet here. And the angle of the projectile tells us about what the X and Y initial velocity components are going to be looking like. So let's look at this here. So the initial velocity angle depends on V initial X and V initial Y. Of course it does. But what it tells us here is it tells us whether we have a steep shot or whether we have a shallow shot. So in the first situation, we could imagine that we're going to have a very steep initial angle. And what I mean by that is that when I look at this, we can clearly see that if I have a steep angle shot, let's say that it looks something like this here, what you're finding here is that when I project this thing, right? So let's say that this is my initial velocity. If I project this thing onto the y-axis, what you're seeing here is that look at the length of V initial Y and look at the length of Vx. You can see here that V initial Y is going to be greater than V initial X. When this is the case here, right? So if I have a steep initial angle, then this tells me that this must be the case. And if that's the case here, then the angle of this guy, if I go and I calculate this guy here, this guy tells us that it has to be greater than 45 degrees. So it's past the midpoint. Now, the other scenario here is that I'm going to say that I'm going to have, I guess, a less steep, or maybe I'll call it a shallow angle, shallow initial angle, excuse me. And what do I mean by that? Well, let's go look at the picture this time. If I draw the same kind of picture, I'm going to set up my velocity vector like this. So if it's a shallow angle, remember, we're always setting the speed to be 10 meters a second. It always has to look that way. So what you're going to see here is that in this case, the angle looks like this. So if this is my initial speed and both of these have the same length, when I do my projection, look at my X component. My X component is going to look like this. My Y component is going to look like this. So right away, we could see that the length of the X is bigger than the length of Y, like that. So a shallow initial angle immediately tells us that V initial X is greater than V initial Y. So if I go and I look at the angle again, using the exact same tan inverse as I did up there, this angle will be less than 45 degrees. That's what I mean by that. So now let's go to the applet and I'll show you what I mean here. So the first thing that I want to do is I want to do a steep shot. So let's go look at that. So let me set it up right here. And let me show you what I have. So here's this applet here. And what I'm going to do here is that I want a steep angle. So how about if I change this to 75? And what you're seeing here is that I want you to look at two things here. So the first thing that I want you to look at is that look at the components here. Okay. Look at the components. And when you look at the components, you could see that the X and Y velocity components are different. And where you're seeing that is that you're seeing here the components of velocity. You can see that Vx is what, 2.6, Vy is about 9.7. And you could see that the vertical component is bigger than the horizontal component. Now, if I come in here and I change the angle, let's say to 15, you could see that the components are quite different now. And you could see that the X component has reversed in value. And that's sort of like a strange thing, how they have the exact same values as before here. So just as we would expect this thing here, you're getting this sort of like reversal of the X and the Y's here. But what I want you to pay attention to is something different here. So I'm going to come back. So I'm going to start off with the 15 here. And I want you to pay attention to how much time this thing is in there. So I'm going to go into slow-mo. Look at the time it takes for this projectile to actually go, and look at the box here. So if I start this thing, you could see that this thing goes up and then it comes back down. Look at the time. So the time for this thing to go up and down is what? Is about 0.53 seconds. Not very long. So now what we want to go do here is that we want to go in and essentially do the same thing, but with the 75-degree angle. So now let's do, I have to reset, sorry. So here's 75 degrees. So here we go. So look at the amount of time that's in the air now. Yes, I know that this is in slow-mo. I agree. So you can see it's almost like 4 times more. Now, is this shocking? It shouldn't be shocking to you. The question is, why should it not be shocking? So there's a couple of things that I want to bring into my OneNote because I want to go in and talk about a couple of things. And remember, I said that the initial velocity plays an important role in understanding the behavior of projectiles. So here is my OneNote right here. So the first thing that I want you to pay attention to is that I took images while this was going on here. And the first thing I want you to look at is that I want you to look at this here. Look at the velocity components here. The fact that V initial Y is greater than V initial X, that tells you that this is a steep angle shot, as expected. And if I look at these components over here, you could see here that it's the reverse here. And this is because it's a shallow angle that we're shooting this thing at. So no surprise here. But one of the things that I want you to really pay attention to here is that this right here, this is the time in air that the projectile, right? Time in air that the projectile flies. And of course, this is also the time. Now note the difference here. This is, right? This is much much longer flight time, right? This is much less flight time. And what I'm saying here is that the important piece of information here is why. Why is one much longer compared to the other? And the answer is Vy. Think about this thing here. So this guy has a much larger V initial Y. This guy has a much smaller Vy. It's the Vy that really has a lot to tell you about this thing. And what does this mean? And think about this. If you throw a ball with with a larger initial speed, what's going to happen to the ball? It's going to be in the air for a longer amount of time. If you throw it with less vertical speed upwards, it's going to be in the air for less amount of time. So clearly, if you throw it with a larger initial speed, this tells you it's going to spend more time in the air, right? No surprise. But if it spends more time in there, it should go to what? It goes to a higher height. That shouldn't be a surprise to you. But that's exactly what this steep angle is telling you. That because I have a higher initial velocity in the y direction, I've thrown it harder in the y direction, which means it's got to be in the air for a longer amount of time. And of course, it's going to go higher. Whereas if I do the opposite here, so if you throw a ball with less speed, vertically, what does that mean? It's going to spend what? Less time in the air. No surprise. And what's going to happen? It's going to go to a lower height. So anytime you see the components of V initial Y versus V initial X, it's going to give you that detail right there. Okay, so physically, that's what that means here. So what we want to do here is that what you're seeing here is this, that a longer V initial Y tells you two things. It's going to be the air in a longer time, and it's going to go to a higher height. If I have a smaller V initial Y, it's not going to be in the air as long, and it's going to go to a smaller height, a lower height. That V initial Y determines those details here. What we were saying here is that when I looked at the initial velocity, I defined what I meant by a steep angle shot versus a shallow angle shot. Now, I'll probably rewrite what I wrote just to be a little bit more cleaner here. But what you're going to find here is that I start off with some initial speed, okay? And this is my initial speed. I'm fixing my initial speed here. So now that I have that fixed, what I'm going to do then is that I know that every shot that is being shot at is always 10 meters a second, no matter what. So I'm not throwing it harder. I'm not throwing it slower. The initial speed is always the same.
So clearly the initial velocity has to depend on what? It has to depend on its y component and its x component. So that's what we want to go focus on. So if I go and I do that, what you're seeing here is that if I have an initial steep angle, what do I really mean by that? Well, it means that V initial y is larger than V initial x. And when I look at the angle, that means that the angle has to be higher than 45 degrees. And so when you look at this, you could see that the y component in red is bigger than the x component in green. That's what I mean by a steep angle. And then if I go to the shallow angle, that means the reverse, that V initial x is larger than V initial y. But when you calculate that tan inverse, that means that it has to be less than 45 degrees. So the 45-degree line is really the mark. And so what that means here is that, that the initial x component in green is larger than the initial y component. And it turns out that looking at that V initial y really plays a big part. And what I did here is that I showed you this by looking at this applet by Fent. And one of the first things that I asked you to note, if you look at V initial y being the steep angle, you're seeing here that if I look at the y components, you could see that Vy is about 9.7, whereas Vx is 2.6. That's what I mean by a steep angle. Whereas if you look at the other case where the components are reversed, x is much larger than the y one. So what you're seeing here is that when we shot it, we saw that there was more time, right? This point right here, there was more time in the air for the steep shot, and it goes higher. Whereas if I go look at the one that's less than 45 degrees, the shallow shot, you could see that it spends less time in the air and it goes less high. So it's that V initial y that really plays the part here. So if I have a much longer flight time, that means I have to have a higher initial velocity in the y direction. Whereas if I have a smaller, I'm going to have a smaller flight time if I have a smaller V initial y. So it goes hand in hand. But if it goes high, but if it has more time in the air vertically, then it has to go to a higher height. Whereas in this one, because it doesn't have such a big vertical V initial y, it's not in the air as long, and so therefore it goes to a lower height. So effectively what you're seeing here is that if I put more emphasis in throwing it in the y, I'm going to have higher heights, longer flight times. If I don't do that, then I'm going to have lower heights, a shorter flight time. But it really all depends on how much speed you're given in the y direction here. So what I wanted to do here is that to sort of like emphasize this thing, let me organize here. I got to go get one thing. And what I have here is I have an image that I want you to pay attention to. Now, this is an old image that I'm pretty sure I even use it in Physics 11, but I think it's a really powerful image. And I think there's a lot that it's actually telling us that we really want to look at here. So the first thing that I would ask you here is that, let's say I have some object that follows path 1, 2, and 3. All we know is that we have 3 projectiles. Okay. And the question is, what can you tell me about the flight times? In other words, which one is going to be in the air the longest? Or how would you rank them? And the one thing that you want to pay attention to is this. Look at this line. What did all of these projectiles do? They got to the same height. But wait a minute. If they have the same height, we already said that the thing that determines height is what? V initial y. So what this tells us here, because they have the same height, that means that V initial y for 1 must be equal to V initial y2, which must be V initial y3. They have to have the same initial velocities. But wait a minute, right? If that's the case here, we already said here, if they have the same height, they must have what? They must also have the same flight time. So even though they have 3 different motions, you're seeing that the time that 1 and 2 and 3 are going to be all the same. Why? Because they have the same initial velocity in the y direction here. That's really powerful here, right? Just by looking at them, you know that they're in the same heights here. Say the same height immediately tells you that the time of flight is going to be the same here. But you do see something different about them, and you can see here that if you look, this guy has what? Look at this guy. This guy has a distance x1. This has a distance x2. And of course, this has distance x3. But one of the things that we said here is that if you want a larger horizontal distance, you need a larger velocity in the x direction here. So what this tells me here is that if I look at my picture, just by looking at these distances, we could then say here that because we have, so if I look at this guy here, because we have larger, or not larger, but let's say different horizontal distances, that means we know that this is the case here, just by looking at that picture, that horizontal distance. This implies then that the only way to have larger horizontal distance is that we must have different initial x components. So in this case, it should be the velocity initially in the x direction of 3 that should be larger than the initial velocity for 2 and this and on to 1. So that must be the case. So if I start to go and look at the velocities, what do I see here? So if I can now have a picture. So if I look at 1, let's say it looks like this. So this guy's going to be, let me make this a little bit longer. I need to bring it here. So this will be V initial y for 1. And if I look at 2, it's got to be like this, exactly the same. And if I look at 3, exactly the same. What's different, though, has to be the velocity in the x direction. 1, because it travels a smaller distance, should have what? A smaller velocity in the x direction. And then if I look at the next one, because it's traveling farther, it should have a little bit larger. And then finally, this guy is going to be for 3 because it has to be longest. So when I go and I look at the initial velocity of this guy, I use the parallelogram rule. The parallelogram rule tells me what? that is going to be the initial velocity of 1. And if I look at the parallelogram rule for 2, you could see that this velocity is longer than the other one. And if I look at the third, this is even longer. So we could immediately say that the initial speeds of these projectiles must be in this way here. So just picture-wise, it has to be this way. So that's the behavior of the initial velocity right there.